So after seeing how easy it is to integrate a vector, so doing the surface integrals of a vector is very easy because you just have to split it into its components, get the basis vectors outside because they are constant, so you end up having to do 3 integrals, one for each component of your answer, and the answer is a integral, is a vector. Wow, I'm getting good sun now. Great. Anyway, in this video I want to give you a warning. When you do this, so being able to split the integral of a vector into 3 integrals, there is a danger, okay? And the danger is, what if the basis vectors are not constant? So x hat, y hat, and z hat, that's always safe. You can always take them out of the integral. But what if I ask you to integrate a vector, surface integral of a vector, which I write in, let's say, spherical coordinates, and I give you fr in the er direction plus f theta in the e theta direction, and let's say there is no phi direction in this vector times ds. So now you cannot do the trick of assuming that er and e theta are constant and take them out. So this is not equal to er times the integral of fr ds plus e theta hat times the integral of f theta ds. Okay, this is not correct. This is wrong. So how do you do it? You have to convert the basis vectors that are not constant into constant basis vectors. And the best choice is always to just go into Cartesian coordinates, x, y, z basis. Okay? So that's how you do it. For example, imagine that I ask you this, and forget for a moment that you are not seeing this picture, just look at the question. Calculate this integral. Now notice that this is bold, so this is a vector. Okay, so the integral whose result must be a vector because I'm integrating something that has direction, yeah? So it's the integral, the surface integral over ds of the er hat unit vector, okay? And what is the surface? So the surface is the surface of a sphere S. So I'm asking you to integrate er hat vector over the surface of a sphere. So what am I really asking here? If you were naive and just applied blindly the fact that you can take er outside, you would wrongly state that I is simply er times the surface of the sphere, because it's the double integral of ds, which would be 4 pi r squared. Yeah. But this is completely wrong. Wrong. It doesn't even make sense, because how do you interpret this answer? 4 pi r squared in the direction er. What is the direction er? If I don't specify a location, I cannot specify a direction er. Remember, er is always pointing away from the origin. But where are we placing this vector er to point away from the origin? It doesn't make sense. This answer doesn't make sense. Okay? And the reason is that we have to split into x hat, y hat, and z hat before doing the integral, because er depends on where we are along the surface of the sphere. So we cannot take er outside of the integral. Visually, this is what we are doing. So er hat is this arrow that points away from the origin. So this creates like this this bubble fish that inflates and it has spines. Yeah, that's what this reminds me of. So we are saying, okay, integrate this er hat vector throughout the entire sphere. So this is like saying, divide the sphere into tiny areas, calculate er on that area, and do that for every tiny area of the sphere and add up the different vectors. So of course the answer should be 0, because every single vector at any point in the sphere is cancelled out by an identical vector at the opposite antipodal point in the sphere. So the answer to this integration should be 0. And indeed you do get 0 if you split it into components. So the integral of ER hat ds. If you split ER hat into the XYZ basis, and you can look that up in the table for coordinates that I give you in the exam. So ER hat is written as sine theta cos phi times x hat plus sine theta sine phi times y hat plus cos theta times z hat ds. Okay, so now we need to do these three integrals. We need to do this integral, and that will be the x component of the answer. Then we need to do this integral, and that will be the y component of the answer. And we need to do this integral, and that will be the z component of the answer. And each of these integrals, if you do them for the sphere, you get 0 plus 0 plus 0. So indeed, they all cancel out, as we expected. Okay? If you want to try an exercise, maybe you could try integrating ER, but only on the upper half of a sphere. Okay, so only on the upper half. So then your intuition should tell you that the x component and the y component of ER should always cancel out, but you should have a net z component. Okay, so try it out, do this integral in half of a sphere and see what the result is. It should be only oriented along z. Okay? Very good. So, see you in the next video.